Hi, my name is Lisa Oakley, and I'm presenting my work with Professors Alina Oprea and Stavros Tripakis on adversarial robustness verification and attack synthesis for stochastic systems. Our work is based on the field of model checking for stochastic systems, which is a useful tool for evaluating properties of systems with probabilistic transitions. Some of these systems include Markov decision processes or Markov chains. Examples of systems that can be modeled in this way are things like a robot navigating a warehouse, where the robot may have probabilistic decision-making on which direction to go, or a communication protocol that has a probabilistic mechanism to determine how often to send a message. These models typically rely on an accurate representation of the underlying system and assume certain system transitions. Oftentimes, these do not consider an adversarial deployment environment where the actual system transition probabilities are different from the model. So we can give an example of this sort of thing by this simple communication protocol. This is a 4-state discrete time Markov chain where you have the start, try, lost, and delivered states. And the weights on the edges between nodes in the graph represent the probabilities of those transitions occurring. So we can see here that the probability that the system reaches the delivered state within 4 time steps can be computed by adding together the probabilities of the paths that satisfy this property. So here we have the start to try to delivered state is a path that satisfies this property that occurs with 9/10 probability. And then the start to try to lost to try to delivered path is the other path that satisfies this property, and that occurs with 1/10 times 9/10 probability. So we have overall that the probability that the system reaches the delivered state in 4 time steps is 99%. However, we see that if we have an adversary who's able to modify these system transition probabilities, the actual result on the overall system utility is similarly accumulated to the way that the original probabilities were accumulated. So we can see here that modifying one edge in this case actually has an effect on each term. And so the resulting probability is now 91%, where it was 99% before, after the adversary has just modified the transition probability of one edge. Our goal is to develop a definition of adversarial robustness in stochastic systems such as these, and develop a framework to verify robustness in the case of an adversary who's able to perturb system transition probabilities. We also want to be able to find the worst case adversary and see exactly what kind of perturbations are causing the system to fail. Some background on the field of probabilistic model checking. So in our work, we consider both discrete time Markov chains and Markov decision processes, but for the purposes of this presentation, we're just going to look at the Markov chains. So a Markov chain is defined by a set of states, for example, start, try, lost, and delivered. An initial state, here we have the start state, and then what is called a transition probability matrix. And this represents all of the transitions in the system and what probability they occur. So each row and each column indicates a state, and then the entry in the matrix represents the probability from transitioning from one state to the other state. We're going to be looking at logical properties to determine the utility of the system. And so we're going to use a similar modeling language as LTL. And some example properties in LTL are eventually reaching the delivered state, always being in the lost state, visiting the delivered state infinitely often, or reaching the lost state within 10 time steps. So in a traditional model checking problem, we would be looking at whether or not each of these properties is satisfied in the system. However, when we're looking at probabilistic systems, we actually have this added feature that we can look at the probability that certain properties are satisfied rather than just looking at whether or not they're satisfied. So in some cases, the probability is 0 or 1, but in other cases, such as the probability that we reach the lost step within 10 time steps, is 0.271. And so here we can see that an adversary modifying the system can not just change whether or not a property is satisfied, but it can change the probability with which a property is satisfied. So we are looking at PCTL star as our modeling language, and PCTL star can define properties that have this probabilistic operator, where we're looking at whether the property phi is satisfied with probability in some interval j. So basically, we're seeing if the probability that the system satisfies the property is in this interval. And for our purposes, we're actually going to look at just this probability on its own rather than whether it's in an interval. And this is something that most of the probabilistic model checking tools that exist can compute this probability directly. So our problem definitions begin with a definition of robustness, and specifically adversarial robustness. So in this case, we're looking at a specific Markov chain C. And the Markov chain C can be modified by an adversary to be anything within a predefined perturbation set PS. And so the perturbation set is the set of all of the potential Markov chains that are the result of a perturbation by the adversary. So we might say a Markov chain that shares, 3 transition probabilities with the original Markov chain, but can vary in any other way, something like that. And so what we're looking at is the probability that any perturbed Markov chain in this perturbation set, the difference between the probability of the perturbed Markov chain satisfying the property and the probability of the original Markov chain satisfying the property should not be greater than some delta. By defining the perturbation set in this way, we are able to then define specific threat models by giving constraints on these perturbation sets. So in our paper, we look specifically at one set of threat models, which are the L infinity or L max threat models. And so in these threat models, we're looking at adversaries who can modify the original Markov chain within an epsilon ball around each transition probability. And so we set some small epsilon, and for every different transition in the system, they're able to modify that transition by the epsilon. And then we look at a more restrictive set of classes that provide different vulnerable transition sets. And these sets of vulnerable transitions are the ones that the adversary is able to control, because it's unlikely that an adversary is going to be able to control every transition in the system, but we can constrict that and give them a budget for each transition. So here are some examples where the original Markov chain is at the top here. And we're going to look at the left-hand side first. So the top left here is the structure preserving selected states adversary. And so under this threat model, an adversary can modify the transition probabilities for a set of transitions that all come from a specific state. And so here we see that state 1 is vulnerable. And so all of the edges that come out of state 1 are able to be attacked. And we're still in this L max threat model where the attack is limited to a budget of epsilon for each edge. And then in the bottom left here, we have a similar threat model that's a structure preserving selected transitions threat model, where we give a set of transitions more explicitly, such as here, the transitions that go between states 0, 2, and 1. And those are the vulnerable states, again, within this epsilon ball around the original transition probability. And this is an area of research called perturbation analysis in Markov chains. And this has been researched pretty well, and there's a lot of different techniques for doing this sort of thing. We also want to consider the case where there is not this structure preserving property. So if we look on the right-hand side here, we can picture a world where an adversary is able to actually change the underlying structure of the Markov chain. For instance, if a robot is only supposed to go up or down, maybe there's a world where they open an avenue for it to go to the side, and we want to be able to model that if we think that that's a possible thing that could happen in the world. And so here we have the selected state attack without that restriction that there's a structure preserving quality. And so you can see that here an adversary is able to add a transition from state 1 to state 2, which can lead the robot into a hazard state where it wouldn't have been able to in the original. And here in the worst case selected transitions attack, we can see that again, within this restriction of which edges are able to be attacked, we can see that it can add an edge, again, leading to the hazard state. So these are kind of the threat models we're going to look at. You can define this perturbation set in any way. And if you use a different distance metrics, for instance, L1, you can actually define a completely different adversary. In the case of an L1 adversary, it would be applying a budget over the whole matrix rather than an element-wise budget. So our verification problem is essentially saying, you're given a Markov chain, you're given this perturbation set, or like the threat model definition, you're given the delta, which is how much we're willing to let the utility decrease. You're given this PCTL star formula that is telling you sort of what property do we care about. And then we are verifying whether or not the worst case attack on the system violates this delta threshold. And since we're looking at this perturbation itself, we realize that we can extract the perturbation matrix to be this X matrix. So we start with the original transition probability matrix of the original Markov chain, and we add this perturbation matrix X. And the perturbation matrix can actually be considered as the adversary itself. And this is really useful because we can both find the worst case perturbation matrix and figure out what the worst case adversary is actually doing. We can also look at which system transitions are being affected the most, and that can help us determine which parts of the system need the most security. And so the problem that we're going to solve, which will actually solve the verification problem, is the problem of synthesizing the worst case attack on a Markov chain. And so here what we're doing is we're trying to find the perturbation matrix, which minimizes the probability that the property is satisfied in the perturbed Markov chain. And so we can model this as an optimization, which is finding this perturbation matrix X, which minimizes this probability. And the objective function here is the probability of satisfying the property with this perturbed Markov chain. And then the constraints are just that the Markov chain is within the perturbation set. And for the L infinity or L max threat model that we're looking at throughout this paper, that induces a linear constraint, which helps us apply different optimization methods. So all of the solutions that we're going to present are based on this optimization and use traditional optimization techniques to find a solution. So we have two main solutions, one which uses a direct computation of the objective function and one which pre-computes a symbolic representation of the objective function and then runs the optimization on the symbolic representation. So let's start by talking about the direct computation solution. So in this solution, we are actually going to use a gradient method to solve this optimization. And we're going to compute the objectives function at every stage of the optimization using a probabilistic model checker such as Prism, Storm. And so here we run a gradient method, which then at every step of the gradient descent will compute this value using a model checker. It will actually build the model of the perturbed Markov chain, give the property, and run the model checker on it. So an example here of running the model checker, if we have this Markov chain that we had at the beginning, we can explicitly write out the model with these probabilities, and then we can give the property here, and then it will compute the probability for us. And so basically every time we are picking a new perturbed Markov chain, putting it in the model checker and getting the result. This puts a lot of computation in the objective function, which we have to run a lot of times throughout the optimization. So we tried to think of a way that we could avoid doing all of this computation at every step of the optimization. And there actually turns out to be a way for some properties to pre-compute a symbolic representation of this objective function with parameterized Markov chain that we can then instantiate with different values to get the perturbed versions of the Markov chain. So here we have a parametric discrete time Markov chain where we take the original Markov chain and we replace its entries with parameters. And then we get this C sub X, where X is the set of parameters in the system. And then we have this probability transition matrix, Px, that is symbolically defined. Then we can find this F sub phi of X, which is the probability of satisfying the property in the symbolic case. And this is really useful because then when we're running the optimization, we only are looking at this symbolic representation of just like a function, and we can just instantiate and then compute the function, and that is a very fast operation. So we have pseudocode here for what we're doing, which is basically first taking the original Markov chain and constructing a parametric representation of it. Then we generate this symbolic solution function, and then we solve the optimization using this solution function as the objective. And so in this way, we're giving more pre-computation steps, but the objective function is going to be easier to compute. And so we look at our results, and when we compare these two solutions, we actually get a bit of a surprise. which is when we have large numbers of states and parameters, the direct computation method is actually faster. So let's look a little bit more closely at this. The duration column here on the right-hand side in bold, we have the total duration of each method for computing the solution. And we see that for 25 states and 5 parameters, the symbolic solution function is faster than the direct computation. But we see that even if we go to 10 parameters and 25 states, we see that the direct computation method takes less than 3 seconds and the symbolic solution function takes 125, which is kind of surprising. So we break it down and we see on the right-hand term, we have that it takes less than a second to do the optimization. But we see on the left-hand term that the pre-computation step takes 124 seconds. And this is because these tools to find the symbolic solution function are typically used on systems that have maybe 1 or 2 parameters. But when we're looking at an adversarial attack, we want to be able to model an adversary who has more power than just changing 1 or 2 edges in the system. And so for our purposes, we're going to use the direct computation approach because it scales a lot better when we have these like large parameters and numbers of states, where we see that the symbolic solution function is timing out for even 25 states and 20 parameters. And we see that for 225 states and 20 parameters, direct computation actually takes less than 300 seconds, which is actually pretty good, considering that we're running a model checker at every step of the optimization. And now we want to look at actually what our tool is doing. And so on the left-hand side, we have here a similar protocol to at the beginning of our presentation. And we see that an adversary who maintains the structure of this protocol and is given an increasing budget, which is along the x-axis, we see the budget increase. We see that the probability of satisfying the property, which is on the y-axis, starts to decrease dramatically, even by just modifying the transition probabilities that come out of the tri-state. And so we see that this compounding problem, where you modify one edge and it compounds as you compute it, we see that as we give more budget to the adversary, they're able to reduce the utility of the system pretty significantly. We also can use this to look at things like here we have the IPv4 protocol, the collision avoidance part of it. And here we have a node entering a network, and the node generates an address and then broadcasts the address that it generates to all the other nodes in the network. And the probabilistic portion of this is that it waits for a response from the nodes for a amount of time that is probabilistically determined. And here we see that if the adversary is able to early on in the time frame prevent a node that is entering the network from receiving the message that they have a conflict, we can see that if you do that earlier on, which is represented by this yellow line, that the adversary is able to decrease utility more than if they are able to prevent this message from being sent later in the protocol, which is what happens in this blue line with the diamonds. So this tool is also useful because you can change the adversary's ability to modify transitions in a system, and you can see sort of which adversaries are more or less able to affect the utility. There are also some situations where we might want to consider these non-structure preserving adversaries. So for example, the grid world case study considers a robot that's moving around a grid that can move up, down, left, or right. And it might run into some hazard states, and it might be trying to reach some sort of goal state. And so here we can see an example of one of these grid world. And so on the right, you can see an example of a grid world where the probabilities indicate moving around a grid with some probability. And so an attacker who has access to the states 1, 3, and 7 and is able to modify any transition coming out of those states, we see that in a structure preserving case, they are very restricted in what they're able to do. So for example, in state 1, which we see across here, this is the perturbation matrix, and this is the original probability transition matrix. In the perturbation matrix, we can see that in state 1, all it can really do is add to the transition going back and take away the probability that the transition goes toward the goal. And you can see that like in each of the cases, it's doing that. And for state 3, you can see that it's actually adding probability to the chance that you go to the hazard state, which would violate the property that we're trying to avoid, the hazard state. But we can see here that in the non-structure preserving attack, the adversary is able to, for example, in state 1, take this completely unconnected hazard state that exists here that wouldn't even be considered in the original computations. And it's able to create an edge between state 1 and state 2. And it adds probability that it's able to move from state 1 and state 2. And that is a direct way of reducing the utility of the system. And so we might want to consider something like this if we have, say, a robot that's moving through a warehouse and somebody's able to like open a door to a stairwell or something that could fall down. Like we want to be able to model situations that we might not have considered in the observation, or that might not have occurred when we were running simulations, but that might occur if we have an adversary. And we see here that in both cases, the probability of satisfying the property when given more budget decreases much faster and with less budget when the adversary is able to modify these underlying structure of the system. And so it's something that I think is very useful for system analysis. We want to briefly mention a connection here to adversarial machine learning that is a very interesting one because we believe there is some prospect of using this for those sorts of problems. So there's certain stages to a supervised machine learning algorithm. The training stage, which uses data drawn from a distribution to learn a function, such as a neural network. The validation stage, which computes function loss on new data drawn from the same distribution. And a deployment stage, which uses the model on a real-world task. In stochastic modeling, there's actually a similar set of stages. The training stage is determining the assumed structure and probabilities of a system via observation. And then the validation stage is computing the utility of that system as a probability of satisfying a logical property. And we have a similar thing here where in the supervised machine learning case, we're assuming this underlying distribution. And in the stochastic modeling case, we're assuming this system transition probabilities. And in the deployment stage, we're using this model on a real world task that might not actually reflect those assumptions that exist in the training and the validation. And so there's something between validation and deployment where the adversary can undermine these assumptions and without doing something that would be obvious, can make a pretty significant impact on the model's performance on a real world task. So we can look at it similar to adversarial examples in adversarial machine learning. So on the bottom here, we have an adversarial example, which takes the original image of a panda, and then it runs an optimization to find a perturbation of this image in order to create a new image that the model classifies incorrectly with high confidence. And so we're doing a similar thing here, where we're taking an original system that's assumed or learned from some data, and then we are running an optimization to find a perturbation of that system that would most decrease utility. And then we have this new system that might not look very different from the old system, but because of this compounding issue of the way that you compute these probabilities, we see that it might have a pretty significant impact on system utility. In conclusion, we introduced a set of formal definitions for adversarial robustness in stochastic systems and developed a framework for assessing the robustness of discrete time Markov chains and synthesizing worst-case adversaries. In the future, we'd like to utilize these robustness definitions and verification framework to verify systems with machine learning components. This could be particularly interesting for things like deep reinforcement learning that actually use Markov decision processes as a theoretical background. And we want to extend the framework to include more complex threat models, for example, attackers that can dynamically choose states or who have a budget that they can put over all of their vulnerable transitions. If you have any questions or comments, I'll be available on Zoom for 5 minutes to talk to you all. And if you have anything else, you can feel free to email me at oakley.l@northeastern.edu. I'd be happy to hear from you. Thank you so much for your time.